We'll move on with the program. Qian Zhang, PhD researcher from the University of Stavanger. He will be giving a presentation on techno-economic performance of a PV battery-centered microgrid based on price-based operation strategy. Qian, can you hear us?
Yes, I can hear you. Can you see my screen?
Yes, we can hear you. We can see your screen. We can see you. If you can put it in presenter, perfect.
Okay, yes.
The floor is yours.
Okay, thank you. And I'm ESR9. My name is Qian Zhang, and I joined University of Stavanger last year. And I'm going to present some results of this year. And my PhD topic is about development of a real-time optimization solution for the integrated energy systems. And currently we're focusing on the microgrid level. And as defined by the US Department Energy, and microgrid is a group of interconnected load and distributed energy resources. And the microgrid can act as a single controllable entity, and the microgrid can also disconnect with grid to run it as an island mode. Here is the schematic of microgrid, and we can see here it is the supply side. It may include the PV panel, wind turbine, and here we can see the storage side. It can include battery or other storage technology, and it also includes the demand side. And the microgrid can integrate with the main grid. And the core of the microgrid is the EMS. It is the energy management systems. And why we research microgrid? Because microgrid can run in the island mode. It will be suitable for the rural region, and the microgrid can also reduce the transmission and the distribution cost. And it also offer because microgrid can run in a very flexible way, and it offers the energy efficiency by responding to the real-time market price. But we also meet a lot of challenge for microgrid in the design phase, because there are so many types and so many types of generation and storage technology, like PV, wind turbine, microgas turbine, etc. And we need to decide which type and the size of the technology. And we also need to meet the energy efficiency and the economic development, this kind of requirement. And in the operation phase, we also need to decide when to run and stop the equipment and how much capacity each equipment should generate. And we also need to decide when to charge or discharge the storage technology. And finally, we want to get the minimum operation cost and emission. Here I list the two example scenario. The first one is like an organization want to already get the specific location, and they have some renewable generation target. It will be the 30%. And how should they spend their limited capital resources to get the goal? And another scenario is organization interested in PV and energy storage. They want to know whether this kind of combination economic feasible, and if so, how should they operate the energy storage? Here we are going to develop a toolbox to answer the questions in these scenarios. Here is the methodology, and it will start from modeling, and we are going to develop a model for various technology. It will include PV, wind turbine, microgas turbine, etc., battery, thermal storage. And then we will have some operating strategy like load following, cycling charging, combined dispatch, and predictable control. And with the help of the operation strategy, the energy system can run for 1 year, usually 1 year. And then we will get the simulation, and like the dispatch result. It can be hourly or in the minute level. And we can also get economic and emission results. And then the simulation result, part of the simulation result will be regarded as the optimization variable objective. And then with the help of the optimization algorithms, we can get the optimal sizing solution. For the modeling, here we consider both physical based and the data driven. Physical based, we are going to use the modelic language. And here it is one application of the methodology. It is techno-economic performance of a PV battery centered microgrid with price-based operation strategy. Basically, it is a sizing method for PV battery systems. And here, I consider the location in Cardiff in UK, and it is applied for a residential house. Here we can see the electricity load for 1 year and the weather information for 1 year. It includes the ambient temperature and the solar irradiance. And here is the electricity during the day. I got the data from one paper, and during the beginning of the day, the price is the lowest, and during the afternoon, it is a peak time of the electricity price. And here are the two main component information. And the first one is PV. I got this PV information from a Japanese brand, and this is the main parameter of a battery. Because we need to run the PV battery for system for 1 year, so we need to have some operation strategy. Here I will compare two different operation strategy. First one is load following. The second one will be the price-based strategy. Okay, for the load following strategy, the strategy will start from compare the PV generation and the electricity load. If the PV generation is higher than load, so the strategy will consider to charge the extra power to battery. But before that, the strategy will compare the SOC with the maximum value. If the SOC is lower than the max value, then the power will charge into battery. But if the SOC is equal to max value or higher than max value, the actual power will be wasted. Coming to the starting point, if the PV generation is lower than electricity load, the strategy will consider to discharge the power from the battery. But before that, the strategy also need to compare the SOC with the minimum value. If it is lower than the minimum value, it means the battery cannot discharge because it will hurt bad for its health condition. So strategy will decide to purchase electricity from grid. But on the if the SOC is higher than the minimum value, then the battery will discharge to meet the electricity demand. And for the price-based strategy, there are main difference. The first one is here. This new strategy always compares the strategy SOC with the max value, and if at the same time if the price electricity price is lower than the set point, and the battery will be charged. And another difference is here. If the SOC is lower than the mean value, and at the same time, if the electricity price is higher than the set point, the battery will discharge. Basically, this new strategy can charge the battery during the low price and discharge the battery during the high price. Here is a model. This is a developed in the Modelica environment. And here is the operating strategy. Here is the economic calculation. And for the optimization part, the objective will be the life cycle cost. It will be 25 years cost, and it will include the PV capital fees, operation and the maintenance fees, and the battery capital fee and the replacement fee, and the electricity from the grid. And there are two main optimization variables. The first one is PV capacity and the battery capacity. The optimization algorithm will be the SQP, and I use the Daimler optimization library for optimization. Here the optimization result. For the case one, it is a load following. We can get this number of life cycle cost, and on the right side it's price-based, and basically the price-based strategy can save more than 7% of a life cycle cost. And here I list typical day under two operate strategy. The left one is the load following strategy. We can see the blue line is the PV generation, and the green line, the blue line is the PV generation, the green one is the load profile, and the black one is SOC. As we can see, it's the PV generation is higher than the load following load profile, and the SOC will increase until its max value. And if the PV generation is lower than the electricity load, the battery will discharge and the SOC will decrease until its minimum value. On the right side, we can see at the beginning of the day, the SOC will be increased because it is a low price period. And on the afternoon, and the battery will discharge because it is a high price period. Here I list the SOC for whole year. As we can see, for the load following strategy, during the springtime and the winter time, the SOC will always remain the constant because during this time, PV generation will always lower than electricity load. But for the price-based strategy, the SOC will always change. So this kind of strategy can utilize PV, utilize the battery capacity well. Okay, thank you. Thank you for your time. Thank you for listening. This is my presentation.